In the second approximation, Debye and Hückel took into account the size of the ions. For the integration constant A1 in the equation, the following formula was used. And the potential of the ionic atmosphere was defined as the limit. The final equation for the average activity coefficient has the form where B equals the value of A in its physical meaning corresponds to the distance to which the electrical centers of two ions can approach. However, the solvation of ions makes the value undefined. Therefore, the value of A is selected based on the best fit of the formula to experimental data. To do this, you can build a graph in the coordinates. The slope of this plot is equal to A. Thus, the proposed formula is semi-empirical. For aqueous electrolyte solutions, Guentelberg proposed writing this equation in a simpler approximate form. The advantage of this formula is that it does not contain arbitrary constants, and at the same time will describe the behavior of many electrolytes up to an ionic strength of 1/10. The second approximation of the Debye-Hückel theory makes it possible to expand the range of concentrations of its applicability. However, in the second approximation, it is impossible to completely describe the entire range of the dependence of the activity coefficient on concentration. So, for large values of the ionic strength of the solution, the value strives for a limit equal to. On the other hand, the experimental values of the activity coefficient at high electrolyte concentration begin to increase.